in Maths, Sita College, Tiruchirappalli. In this video, I am going to give an idea about continual fraction of the ratios of consecutive polygonal numbers. In ancient Greek, mathematician Dept was one of the first to study polygonal numbers. A polygonal number can be defined as a sum of equidistant dots used to represent a polygon of a certain size. Here, identify the patterns of continual fraction of ratios of polygonal numbers of consecutive size. A square number with rank 1 is 1, rank 2 is 4. Because we expand the length and width by 1 dot each and fill in the outer layer, then rank 3 would be 9, and it continues in this fashion. The rank of a polygonal number is the number of dots on a side of the outermost layer of the polygonal number. The polygonal number is denoted by PD of n, where p is the number of sides to the corresponding polygon and n is the rank or order of the polygonal number. P5 of 4 would be pentagonal number with rank 4. All polygonal numbers with rank 1 equals 1, and all polygonal number of rank 2 are equals to the number of sides on the corresponding polygon. Polygonal number of side p and rank n is given by the formula PD of n is equal to d minus 2 into n square plus 4 minus n into n divided by 2, where d and n are belong to the natural numbers. Here, the representation of triangular, square, and rank and pentagonal numbers of rank 3 are given. P3 of 3 is equal to 6, P4 of 3 is equal to 9, and P5 of 3 is equal to 12. Here the values of some polygonal numbers are given here. Here the sides of a polygonal number, and first row represents the ranks of the polygonal number. For example, the triangular number corresponding their ranks are given by 1, 3, 6, 10, 15, 21, 28, and so on. The origin of continuous fraction is traditionally placed at the time of creation of Euclid's algorithm. Due to its close relationship to the continuous fraction, the creation of Euclid's algorithm signifies the initial development of continuous fraction. Euler showed that every rational number can be expressed as a terminating simple continuous fraction. He also provided an expression for E, and he shows that it is irrational. Any finite simple continuous fraction represents a rational number. Conversely, any rational number can be expressed as a simple finite continuous fraction expression. Euclid's division algorithm. Euclid's division algorithm is a repeated algorithm of division algorithm. Any rational number p by q can be represented as a0 into q plus r0. That is, whenever p is divided by q, we get the quotient a0 and remainder r0, where r0 is lies between 0 and q. If r0 is not equal to 0, then q is equal to a1 plus r0 plus r1. That is, q is divided by r0, we get the quotient a1 and remainder r1. Proceeding in this way until we get the remainder becomes 0. Suppose the nth remainder rn equal to 0, then we have rn minus 2 is equal to an into rn minus 1 plus rn. This is the continuous fraction expression. That is, any rational number of the form p by q can be expressed as a0 plus b0 by a1 plus b1 by a2 plus b2 by a3 plus b3, etc. Here a0, b0 belongs to real or complex numbers. Here, this is a simple continuous fraction expression. Here, we note that all b's are equal to 1. Therefore, this is said to be a simple finite continuous fraction expression. This is the general form of continuous fraction expression and simplest form of this expression. The elements a0, a1, a2, etc. are called the partial quotients. If there are finite number of partial quotients, we call it as simple continuous fraction. Otherwise, it is an infinite simple continuous fraction. If a finite simple continuous fraction is denoted by a0, a1, a2, etc. an, and the alternate form of this can be represented by a0, a1, a2, etc. an minus 1, comma 1. This is a continuous fraction algorithm. Suppose we want to express a rational number is a continuous fraction expression. Let us take the initial value x naught is equal to x and the a naught is equal to integral part of x naught. Now we define x1 is equal to the reciprocal of x naught minus integral part of x naught and say a1 is equal to integral part of x1 and x2 is equal to reciprocal of x1 minus integral part of x1. Therefore, a2 is equal to integral part of x2. Proceeding in this way until we get xi belongs to n, that is belongs to the natural number. This is an example of a continuous fraction expression, that is any rational number can be expressed as a finite simple continuous fraction. So here we consider the rational number 414 divided by 283, which is equal to 1.4629, whose continuous fraction expression is 12645. Let us say one of the irrational number root 3 and root 7 are represented by 1, 1, 2, 1, 2, 1, 2 and 2, 1, 1, 1, 4, 1, 1, 1, 4. This is known as a periodic continuous fraction and it is also denoted by 1, 1, 2 periodic and 1, 1, 1, 1, 4 periodic. This theorem shows that the continuous fraction of ratio of consecutive polynomial number of rank 2 is 0, 1, d, where d is the sides of the polygon and d greater than or equal to 0. That is, pd of 2 divided by pd plus 1 of 2 is equal to 0, 1, d, where d greater than or equal to 3. Proof of this theorem is using on induction on d. Fix n is equal to 2 and d equal to 3. pd of 2 divided by pd plus 1 of 2 is equal to 3 by 4. Using continuous fraction algorithm, let us take x naught is equal to 3 by 4. So a naught is equal to the integral part of x naught is equal to 0. And take x1 as the integral part of, that is reciprocal of the integral part of x naught minus integral part of x naught. So we get 1 by 4, 1 plus 1 by 3. Therefore, the integral part of x1 is nothing but a1. Let us take a1 is equal to 1. And again x2 is equal to reciprocal of x1 minus integral part of x1, that is 3. Therefore, a2 is equal to 3. Therefore, p3 of 2 divided by p4 of 2 is equal to 3 by 4, that is 0, 1, 3. The result is true when b is equal to 3. Next, let us assume that the result is true for d equal to k minus 1, where pk minus 1 of 2 divided by pk of 2 is equal to 0, 1, k minus 1. Now we have to prove that the result is true for d equal to k, that is pk of 2 divided by pk plus 1 of 2 is equal to k divided by k plus 1. So k divided by k plus 1, whose integral part is 0, therefore a naught is equal to 0. And let us take x1 is equal to reciprocal of x naught minus integral part of x naught, that is 1 plus 1 by k. So that integral part is taken as a1, that is equal to 1. Proceeding in this way, the continuous fraction expression of pk of 2 divided by pk plus 1 of 2 is equal to 0, 1, k. Therefore, by induction, we have proved that pd of 2 divided by pd plus 1 of 2 is equal to 0, 1, d, where d greater than or equal to 3. Next theorem proves that the ratio of the consecutive polynomial number of rank 3 is 0, 1, d minus 1, where d is the sides of a polynomial and d greater than or equal to 3, that is pd of 3 divided by pd plus 1 of 3 equal to 0, 1, d minus 1, where d greater than or equal to 3. Next theorem proves that the continuous fraction of the ratios of consecutive polynomial number of sides d greater than or equal to 3 and rank greater than or equal to 4 is pd of r divided by pd plus 1 of r is equal to 0, 1, d minus 2, r minus 1 by 2 if r is r, 0, 1, d minus 2, r minus 2 by 2, 2 if r is even. In this video, we have identified various patterns of continuous fraction of ratios of polynomial numbers of consecutive sizes. This may be extended to higher order figure eight numbers like a pyramidal number. hope this video gives an idea about control fraction expression and how to find the ratio of the polynomial numbers like triangular number, square number, and so on. Thank you for watching this video. Thank you.